Our next step in calculating z-scores is to characterize the dispersion of the test scores that we're working with. Our data is in the table to the right. We have a column, an ID column, which has the labels for the 5 people who took the test. We have a column for the obtained scores x. We have a column for the mean, which we calculated earlier, which is 2. And we have a column for the deviation of the scores from the mean, and we obtain those by subtracting the mean from each score, each individual score. Now we're ready to go. Dispersion refers to the scatter of scores around the mean, as shown below to the right. Our center point, or mean, is at 0. By dispersion is meant that the scores don't all sit at the 0 point, although they might in some instances. Rather, they deviate from 0 to a greater or lesser degree, and we want to be able to characterize that degree of dispersion. Now x, the deviation score, represents each original score's deviation from the mean. So for example, person 1 deviated -1 from the mean. Their score of 1 was 1 below the mean. Person 4 deviated 0 from the mean, to pick a second example. And as a third example, person 5 deviated 2 from the mean, was 2 points above the mean. So we have our column x of deviation scores, which is the rightmost column of the table below, and also a pictorial representation of the same to the right. And each of these are depictions of the dispersion of the scores. Now let's seek a statistic to characterize this dispersion. We have several possibilities worth exploring. These include the range, the average deviation, the average absolute deviation, the variance, and the standard deviation, and all of these are used at one time or another, well, maybe with one exception we'll see in a moment. The range is calculated by subtracting the lowest from the highest scores. So range equals maximum score minus minimum score, or in this case, that would be 2 minus -1, or 3. The range is a useful characterization of the dispersion of our scores, and it's also handy to calculate because it helps ensure that no scores have mistakenly entered into the set of numbers during a computation, as sometimes can happen in programming errors. For example, we might use a score of -999 as a missing value, and we want to make sure that that's not part of the range. Well, another way to characterize the dispersion might be to calculate an average deviation. That is, we could look at the column with our deviations, the -1, the 0, the -1, the 0, and the 2, and we could figure out, what is the average deviation? I've done the work to the left, and you can see that the numbers sum to 0, so the average deviation is 0 also. And this is always the case because the scores are deviations around the midpoint. So the average deviation isn't going to get us very far. Another option is to calculate the average absolute deviation. To correct for the problem that the average deviation always equals 0, we can instead take the average of the absolute values of the deviations. The absolute values are the unsigned numbers, neither positive nor negative. The absolute values are shown in the column marked x, with the bars on either side. We sum them and divide by n, and that gives us 1 plus 0 plus 1 plus 0 plus 2 divided by 5, or 4/5, which is equal to 0.8. The average absolute deviation tells us that the average person scored 0.8 from the mean. It's handy because it's reported in the units of the original test, and it's readily understandable. Here's a further alternative. Instead of taking the absolute value of the scores, we could square them and then get the average of the squared values. That is the variance. In this case, I've made a column for the squared values, and if we add them up, 1 plus 0 plus 1 plus 0 plus 4, we're going to get a sum of 6. Divide again by the number of observations we have, which is 5, and that's going to give us a variance of 1.2. The equation for the variance is shown underneath the table. One of the issues with the variance, however, is it's difficult to understand or even to put into words. It's the average of people's deviation from the mean in squared units. Why are we calculating that? It sounds a little bit complicated, and we're not used to thinking in terms of averages of squared units. One way to correct for that a little bit is to use a standard deviation, and that's where we take the square root of the variance. The variance was 1.2, so in this case the standard deviation is 1.095. But it's still not very easy to understand. But the standard deviation is closer to the original units of the scale. The standard deviation is symbolized as sigma. So we've now looked at several measures of dispersion. We've looked at the range of these deviation scores, which was 3. We've looked at the average absolute deviation, which was 0.8. We've looked at the variance, which was 1.2. And we've looked at the standard deviation, which is 1.095. All of these statistics are useful for various purposes in test theory. To calculate the z-scores, however, we will use the variance and the standard deviation,